we can combine this ASK, FSK and PSK, amplitude shift keying, phase shift keying and frequency shift keying. These schemes can be combined and we can use more levels to transmit more bits per symbol. That is not only 01 but 0011 or 00001 like this. See, frequency and phase, they are related. So only one of them, either frequency or phase, can be modulated at a time because they are related, because frequency is nothing but the rate of change of phase over time. So either you can take phase or frequency. Let us say we are taking phase. So the amplitude and the phase, these are modulated in combination. You know why we are not using frequency? Because only one can be taken. But phase is, this amplitude is different. So in this figure, if you see, we have 4 dots. These 4 dots are equidistant and at an angle of 45 degree from the positive x-axis. This is 45 degree. What is the angle of this second one on the second quadrant? It's 135 degree. In the third quadrant, 225 degree. Fourth quadrant, 315 degree. So now we can represent four symbols. So that symbol can be 2 bits because 2 to the power 2 is 4. Okay. So the phase of a dot is indicated by the angle aligned from it to the origin, make it with the positive x-axis. The phase is like this. The amplitude of the dot is the distance from the origin. Now this kind of diagram, you see dotted diagram, this is called a constellation diagram. So now in A you see 4 dots, in B you see how many dots? 14. So as I said, here 2 to the power 2 is 4. So at the same time you can send 2 bits per symbol, 0, 0, 0, 1, 1, 1, 1, 0. In this 2 to the power 4 is 16. You can send 4 bit at a time per symbol, like 0, 1, 0, 0 you can send, 1, 1, 1, 0 you can send. 16 combinations are there. So 16 combination, not only about phase, but we are combining the amplitude and the phase I used here. So the modulation scheme can be used to transmit 4 bits per symbol, 4 bit. Okay. This is called as QAM 16 or Quadrature Amplitude Modulation, QAM 16. How does it work? See here. Now let us say we have A as some distance. A can be 1 by root 10. So once we want to send 0, 1, 0, 1. What is the angle? 45 degree. So the phase will be 45. As I said, we are taking the combination of phase and amplitude. What will be the amplitude? The amplitude will be the distance of 0, 1, 0, 1 dot from the origin. Let us say it is A. Okay. So once we want to send 0, 1, 0, 1, this will be like this. Now we want to send say 0, 0, 1, 0. What will be the angle? What will be the phase? The phase will be now, let me just join it. From positive x-axis it is 135 degree. So it will be 135 degree and amplitude can be, you can take the distance, it can be say 3, taking an example. So these are the combination for every bit, for every bit combination, there will be a proper pair of phase and amplitude. This is called QAM 16. Now the third figure you see. This figure is more denser. First one was having 4, then 16, then we have 2 to the power 6, which is 64 dots. So we can have 64 different combination of amplitude and phase. Now we can say send 6 bits per symbol. This bit combination, one of the combination I said. This is called as QAM 64, Quadrature Amplitude Modulation 64. 6 bits can be transmitted per symbol because we have 64 different combination of amplitude and phase. Amplitude, distance from the origin, phase is the angle from the positive x-axis. Okay. Now how do we assign the bits? You can say how these bits are being assigned. Why we have 1, 1, 1, 1 here, 1, 0, 1, 1 there? Why can't we have some other combination? Okay. You can have 1, 0, 0, 0 at the top. Why can't you have it in the third quadrant? The main argument is, the important consideration is that a small burst of noise at the receiver may not lead to many bit errors. So assigning consecutive bit values to adjacent symbols, that is what we do. For example, in say QAM 16, let us take the example of the second figure. If one symbol, say it is 0, 1, 1, 1, and the neighboring symbol is, for example, 1, 0, 0. If the receiver mistakenly picked the adjacent symbol, the whole bit sequence will be wrong. So the solution is, we assign the adjacent symbol so that they only differ by 1 bit. That is the gray code. Gray code is when two combination, they only differ by 1 bit position. That is called the gray code. So you see here, we have an example. This figure shows QAM 16 constellation gray coded. Now these combination all have only 1 bit as differ by 1 bit, gray coded. Okay. Now if the receiver decodes the symbol in error, it will make only a single bit error because of the gray code.